What is up guys, my name is Alistair and I work as a data scientist. In this video, we will go through different ways in which you can convert your categorical variables into numeric ones before feeding them to your machine learning model. So welcome to Encodings 101. So this is the notebook we will be using in this video and the link to the same will be given down below in the description. Feel free to use this notebook as a reference throughout this video. So the walkthrough has been divided into two halves according to the type of encoding strategy. So we have unsupervised and supervised encoding strategies. We will start with the simpler one, which is the unsupervised encoding strategy. And these are the ones that do not make use of the target variable to encode the categorical variable. So the ones that we will be walking through will be the label encoder, one-hot encoder, frequency encoder, binary encoder, and last but not the least, hashing encoder. So what makes these encoders unsupervised is the fact that they do not utilize the target variable and that they are completely independent from them. So basically the values that we compute for these encoders do not depend on the target variable at all. So when we move on to the supervised encoding strategies, these are the ones that utilize the target variable to encode the categorical column. So the ones that we will walk through today are target encoding, Jamestown encoding, M-estimate encoding, and lastly, catboost encoding. So the supervised encoders are definitely more complex and advanced when compared to the unsupervised encoders. But are they always better? Well, we cannot say because it always depends on the problem you're trying to solve. And these are the libraries that we're going to use in this video. The first one being category encoders. This is available on PyPy, so you can easily pip install it. All the encoders that we're going to walk through in today's video is readily available in this library, so you can just directly import them and use them in your notebooks. The other two libraries would not come as a surprise to you guys because these are the two most used libraries by data scientists, which is NumPy and Pandas. So let's get started by installing all these libraries and let's import all the categories that we'll be walking through. Let's also set a random seed of 42 so that the results shown in this notebook is reproducible. So the dataset that we are going to use in this walkthrough is pretty simple. We have one categorical column and they have three distinct values, which is Ronaldo, Messi, and Neymar. So let's just define it as a list for now. So we will be using two functions offered by NumPy, the first one being np.random.choice, and it will generate a random sample given a 1D array. So it picks and chooses from the category list defined above, and the next one being numpy.random.random, and it will just select you random integers given a low to high range. So what we do is create a data frame with two columns, one which is the player column which contains either Neymar, Messi, or Ronaldo, and we have a goals column which has a range between 1 to 50. So we just generate 10 rows with randomly picked values for the player column and the goals column. So if we print out the data frame, this is how it looks like. So we have 10 rows with the player column having either Neymar, Ronaldo, Messi, and we have the goals column with the number of goals between 1 to 50. So let's move on to label encoder, which is probably the most straightforward and easiest to understand. From the category encoders library that we have imported earlier, label encoding can be performed by importing the ordinal encoder class. Using the ordinal encoder class, we just simply pass in the column which we want to encode, in our case the player column, and we call the fit and transform function on the data frame. In this cell, we create a player original column which contains the original values for each player, and we move this column to the left, so it is easy for us to visualize the original value for the player and the respective encoding and the number of goals that they have scored. So this is how the encoded data frame looks like. When you think about the word encoding, the first thing that comes to mind is converting a string to a number. This is exactly what label encoding does. So each of your categories will be mapped to a unique integer, and this would be saved as a dictionary. So as you can see in the encoded data frame, the value Neymar is mapped to the number 1, Ronaldo is mapped to 2, Messi is mapped to 3. So basically, all label encoding does is map a category to an integer. This is what makes label encoding easy to understand. Now let's move on to one-hot encoding. The category encoders library has a one-hot encoder class which allows you to perform one-hot encoding easily. You can see that there's a parameter called useCatNames which has been set to true. So what it does is that it sets the one-hot encoded column name as your respective category name. And then as usual, we just fit and transform on the data frame. So the next cell, we just move the player original to the left as we've done previously so that we can get a clear view of how your categories are encoded. So let's just display the data frame and see what's happened. So we can see that there are 3 new additional columns that have been created containing the one-hot encoded values. So depending on the category value for a particular row, the column value is set as 1 or 0. So as an example, we can see that in the first row, the player original value is Neymar, and the column player Neymar is set to 1, whereas Ronaldo and Messi is set to 0. And in the second row, Ronaldo is set to 1, whereas Neymar and Messi is set to 0. And this pattern is repeated across the data frame. So this is basically how one-hot encoding works in a nutshell. So in this example, we have 3 distinct category values, and one-hot encoding proceeded to create 3 additional columns. So if you have n category values, you will have n new columns, and each of them will have zeros and ones depending on the row value. Now, since we have seen how one-hot encoding works, let's move on to the next encoder, which is the frequency encoding. Using the category encoders library, we can import the frequency encoder function using the count encoder class. So as we can see, the count encoder class, we are passing in the player column which we need to encode, and we are fitting and transforming the data frame as usual. We have then moved the player original column to the left so that we can compare the encoded values with the original one as usual, and we then print the data frame. So you can see the player column contains the encoded values. So what it basically does is that the encoded value depends on the number of times a category value is repeated across the data frame. So in this data frame, Neymar repeats itself 6 times, so the encoded value is 6. Ronaldo repeats itself 3 times, so the encoded value is 3. Messi just repeats 1 time, so the encoded value is 1. It is pretty straightforward to understand. So count encoder or frequency encoder depends upon how many times a particular category value repeats itself across the dataset. So the count encoder or the frequency encoder has an additional parameter called normalize, which has been set to true. Let's see what happens when we set this as true. So what happens is that your encoded value is divided by the total number of observations in the dataset. So in our case, we have 10 rows in our dataset. So the value, for example, let's say Neymar had a count of 6, and the total number of values in our data frame was 10. So the normalized count was 6 by 10, which is 0.6. So the new encoded data frame contains the normalized values for the player column. Now let's move on to the binary encoder. You can import the binary encoder class from the category encoders library as follows. So we fit and transform our data frame as usual, and we move the player original column to the left so that we can compare the encoded values to the original values. And we then print out our encoded data frame. So you can see binary encoder creates 2 new columns. And for Neymar, you set the second column as 1. For Ronaldo, you set the first column as 1. And for Messi, you set both the columns as 1. So this is how we uniquely encode each category value using the binary encoder class. And finally, we move on to the last unsupervised encoding strategy, which is the hashing encoder. We can import hashing encoder from category encoders library using the hashing encoder class, and we pass in the column which we want to encode, and then we fit and transform on the data frame as usual. So when printing the data frame, we can see that hashing encoder has created an additional 8 new columns. So when you observe these 8 new columns which has been created, you will notice that whenever Neymar appears in the row, column 1 is set to 1. Whenever Ronaldo appears in the row, column 7 has been set to 1. And when Messi appears in the row, column 2 has been set to 1. And the question you might ask is, why is there 8 new columns which are generated? Why not any other number? Why not 5? Why not 6? Well, the reason for this is that when we imported the hashing encoder class, we did not pass any values for the n components parameter. So the default value is 8. So the hashing encoder class assigns one of these columns to each category. So for Neymar, column 1 has been assigned. For Ronaldo, column 7 has been assigned. And for Messi, column 2 has been assigned. So if we have new values for a category, another column would be assigned to it, and whenever it appears in the row, that particular column will be set to 1. So the hashing encoder class is very similar to one-hot encoding. The only difference is that with hashing encoder, you have control over the number of columns you create using the n components parameter. Whereas one-hot encoding, the number of columns that have been generated depends on the distinct values present in your categorical column. Now finally, let's move on to the supervised encoding strategies. And as you may recall, Supervised encoding strategies are those that take into consideration the target variable. The encoded column is always a result of some sort of computation applied to the target variable. So let's move on to the first supervised encoder, which is target encoding. Well, you may notice that I'm not using the category encoders library in this example. And the reason for this is to give you guys a basic understanding of how target encoding works in the first place. So if you notice carefully, in this cell, what I basically do is that I compute the average goals that has been scored by each player. So how many goals on average did Neymar score, did Ronaldo score, did Messi score? I compute that and I assign it to the player column. So printing out the encoded data frame, you can see that Neymar has been assigned a numeric value of 16.67, Ronaldo has been assigned 25, and Messi has been assigned 22. What these values are is basically the average goals that has been scored by each player. This is one of the simplest ways in which the target encoding values can be computed. Now let's move on to a more advanced version of supervised encoding, which is James-Stein encoding. So if you look at the formula for James-Stein encoding, you can see that it depends on a B value. So you can compute this B based on the mean of a given category variable I and the mean of your entire target column. You can import the James-Stein encoder class from the category encoders library, and you can fit and transform your input data frame by passing in the target variable in the Y parameter and your entire data frame in the X parameter. After applying the James-Stein encoder formula, you can see that Neymar gets a value of 16.67, Ronaldo gets a value of 25, and Messi gets a value of 22. So you can see these values in the player column, but how do you arrive at these values? So let's do some math to find out. So we have seen the formula for the James-Stein encoder to be 1 minus b times the mean of a given categorical variable yi plus b times the mean of your entire target column. So you can compute this b value based on the variance of a given categorical variable I divided by the variance of your entire target column plus the variance of a given categorical variable I. So let's take the example of Messi. So Messi has one row in our data set, and obviously the mean for the number of goals scored is 22. The mean for our target column goals is 19.7, and the variance for the category Messi is 0, whereas the variance for your target column goals is 148.20. So plugging in these values to the B formula is 0 by 0 plus 148.20, we get 0 obviously. And finally, when we apply the result to the James-Stein encoder formula, we get the encoded value as 22, which you can see in row number 7. So we would be able to derive the remaining values such as 16.67 for Neymar and 25 for Ronaldo if we apply the James-Stein encoder formula. So let's move on to the next supervised encoder, that is the M-estimate encoder. M-estimate encoder is a simplified version of the target encoder which we have discussed previously, where the formula is given as follows. So you take the product of the count of your entire category times the mean of your entire category plus m times mean of your target column divided by the count of a given category plus m, where m is the M estimate, which is defaulted to 1 in the category encoders library. We can load the M estimate encoder class from the category encoders library, and similar to how we have seen in the James-Stein encoder, we can fit and transform by passing the entire data frame to the X parameter and a target column to the Y parameter. And the results are as follows. So for Neymar, you get an encoded value of 17.1. For Ronaldo, you get an encoded value of 23.675. And finally for Messi, you get an encoded value of 20.85. So as we have done previously, let's do some math to come up with how these values are computed. So the M-estimate encoding can be computed by doing a product between the count of a given category with the mean of the given category plus m times the mean of your target divided by the count of a given category plus m, where m is the M estimate. So let's take the example of Messi. So the category encoders library defaults the m value as 1, and we know that the count of the category Messi is 1, as Messi repeats itself one time across our data frame, and the mean of the category Messi is 22, and the mean of our target column goals is 19.7. So plugging in these values to the formula, we can get a value for the M estimate encoding as 20.85 for Messi. This is how Neymar and Ronaldo gets a value of 17.1 and 23.675 respectively. So now, since you have understood how M estimate encoding works, let's move to our last supervised encoder, which is the catboost encoding. If you are familiar with Kaggle competitions, you may notice that catboost encoding is popular among the community. And the reason for this popularity is because of its complexity, as this encoder is time aware, so no random permutations are used while encoding. It makes this encoder sensitive to the ordering of data and suitable for time series problems. And this encoder still works well even if your data does not have any sort of time dependency. You can easily import the catboost encoder class from the category encoders library, and as similar to the previous examples, we can pass in the entire data frame as the X parameter and the target column goals as the Y parameter. So after we fit and transform on our data frame, we can see that Neymar has a value of 19.7 in row number 0, Ronaldo has a value of 19.7 in row number 1, Neymar in its second occurrence has a value of 15.35, Neymar in its third occurrence has a value of 18.23. You may be wondering this is quite different from how the other encoders work, because all the other encoders assigned a unique value for each category. So any occurrence of Neymar had a fixed value, any occurrence of Ronaldo had a fixed value, any occurrence of Messi had a fixed value. But this is not the case for the catboost encoding. This is because catboost encoding depends on the order of the data points in our data frame. So if you look carefully in our encoded data frame, you might notice a specific pattern reoccurring. Neymar's, Ronaldo's, and Messi's first occurrence in the data frame gets assigned a value of 19.7, and I'm speaking about row number 0, 1, and 7. Then we can see the second occurrence gets assigned a value of 15.35. So for Neymar, row number 2 is assigned 15.35, and for Ronaldo, row number 4 is assigned a value of 15.35. So this is why catboost encoding is extremely powerful and is widely used amongst data scientists for encoding their categorical columns. With that being said, I would like to reiterate the fact that there is no one perfect encoder. It always depends on the problem you're trying to solve. Sometimes you may notice that a simple label encoder might perform better than an M-estimate encoder. Or maybe the unsupervised algorithm, which are relatively simpler, works better in general when compared to a supervised algorithm. But this always depends on the problem you're trying to solve. With supervised encoders, there is always a possibility of data leakage, since we use the target column to compute the encoding values. So it is always up to us to experiment and identify what works well for our use case. I hope you guys were able to learn something useful from this video, and if it did, it means the world to me. So please leave a like and subscribe if you have found this video useful, and drop down a comment what you would like to see next. With that being said, I hope you guys have a great day. Take care and peace.